fluid in the reservoir, and I would check that first. Number two, higher than normal hydraulic pump temperature. Remember I told you last week many of the pumps have a feature internally inside of the pump that maintains clearances to a minimum. And in the gear type pumps, what they do is they force high discharge pressure fluid to the flanges of bushings in the pump, and it keeps the bushings in contact with the gear faces. If there's no method to control the internal seepage in the pump, where there's stagnant fluid that can't vacate and provide a flow path back to the reservoir, that'll lead to the pump eventually building up a lot of heat that can't be radiated back to the reservoir for cooling. So again, what I would suspect is the pump is essentially worn out, or at least there's too much clearance, internal clearance in the parts. So might be the cause. Hydraulic pump chatters during operation. This is an indication also of air that's gotten into the inlet of the pump. Maybe you've got a suction line leak that's allowing air to get in. Maybe also the reservoir level is low. But if you hear the pump chattering, again, don't necessarily assume that the problem is with the component. The symptom is that the pump chatters, but again, air might have gotten into the pump at the inlet. Hydraulic fluid flowing from the pump drain line. If the pump is equipped with a seepage drain, and most of them are, this is what it means is that the shaft seal behind the drive shaft has failed. And the detection method that we have on many of the pumps is a seepage drain that's mounted at the flange of the pump. Many of the pumps have 4 seepage drains, and again, the pump manufacturer doesn't know specifically how the pump will be mounted. So the seepage drain at the 6 o'clock position will be left open, and the other seepage drain ports will be blocked or plugged. But if you see hydraulic fluid leaking out of that seepage drain, that's an indication of the shaft seal is broken. Broken shear shaft, well, what I can tell you about that, there's 2 things that cause overloading of the pump. One thing would be is the pump seized internally. Maybe a tooth was broken off of an external type gear pump, or one of the components that internal inside of the pump is jammed against another. That requires an excessive amount of torque that makes the shaft turn, and that of course would cause the shear shaft to fail. So if the pump seizes internally, that's one thing that would cause the shear shaft to bust. The other thing, remember I told you the other item that could cause the shear shaft to fail would be excessive pressure. We normally have an unloading valve, and we also have a system relief valve that are used in the hydraulic circuit. But if those 2 pressure regulating devices have failed, the final straw on pressure regulation will be the shear shaft. So if the shear shaft is broken, it's possible that those 2 other components have failed, and the final straw on pressure regulation, well, we just disable the pump. The shear shaft breaks in 2. So that's what I can tell you, at least a little bit about troubleshooting. Okay? All right, next. This is not necessarily a aircraft pump, but I wanted you to have a little bit of exposure to this particular type of pump. It's called a peristaltic pump. They're not commonly used for aircraft purposes, but you probably have one in your house and you don't realize it. This type of pump is used a lot of times in washing machines. The idea is the liquid that we're pushing with a pump has to be segregated, or at least separated, from the internal working component parts of the pump. And the way that they do it is a kind of a novel idea. They've got a horseshoe-shaped type of rubber tube that's inside of the pump. When the 2 lobes of the pump turn, what it does is it pinches off the tube and traps a quantity of fluid in a section of that horseshoe-shaped tube, and it pushes out the discharge. These are also common pumps that are used in medical applications. When people have to have kidney dialysis, where they have to have blood that's being transfused, or at least blood that's being circulated through filtration, obviously the blood can't be contaminated. So what they do is they have a tube that the blood is kind of contained in. In the case of a washing machine, they do a similar type of deal. The detergents and water itself would be damaging to the internal component parts of the pump, so they keep it separated by kind of enclosing it in a tube assembly that keeps it separate from the rotor itself. So kind of an interesting type of design. The term peristaltic, does anybody know what that means? It means throw up. Okay, so peristaltic. peristalsis, okay? Okay, next, let's talk a little bit about variable displacement pumps for airplanes. These are more commonly used on large commercial aircraft. We'll find them used frequently in multiple places, multiple locations, in Boeing aircraft, Airbus, Lockheed, Douglas aircraft. The big advantage with a variable displacement pump is it has its own method of internal pressure regulation by controlling discharge, how much fluid is actually pushed out of the pump. The device that's inside of all of these pumps that really controls discharge is universally known as a compensator. Anytime that you see the term compensator used with a pump, you can somewhat infer that that particular type of pump is not a constant displacement pump, it's a variable displacement pump. The compensator is really what controls the discharge of the pump, how much fluid is being pushed out of it in order to ultimately control pressure. So it's really an indirect method of pressure control. What I'd also tell you about these pumps as well is you don't require a separate pressure regulator or unloading valve with these particular types of pumps. With these pumps, the compensator really is the method of pressure, internal pressure regulation, again, indirectly by controlling flow or discharge from the pump. And that's what you have. In the circuit where it's used, you will still probably find a system relief valve that's in part of the pressure manifold. The purpose of the system relief valve is just like with any other type of pump system that has a pump. If the compensator should fail, where the system, the flow is unregulated coming from the pump, you still have to have a method of controlling pressure so that the lines don't burst, or at least the pressure manifold doesn't fail. So, but that's the deal. The important thing too is since it has its own method of internal regulation via the compensator, you don't require a separate unloading valve. So again, what that means is you save a little bit of weight and maybe complexity because you only really have a pump with a compensator internally inside of it. The pumps also have certain features that are kind of unique to them. In some cases, we have a dump feature, or at least a disabling feature that will cut off the pump flow intentionally. Let's say we're shutting the aircraft down for a particular reason, or we have to stop the flow from the pump to prevent total loss of hydraulic fluid. So many of these pumps contain blocking valves or features that allow for either depressurization at the discharge of the pump or routing the fluid flow back to the reservoir for emergency purposes. So, but let's talk a little bit about these types of pumps. One of the advantages of variable displacement, fast response to system demand. So with a gear type pump with a pressure regulator, what you're really what you need in that circuit to kind of make the thing work relatively well and not go from kick in to kick out, you're going to have an unload. In addition to an unloading valve, you're going to have an accumulator to prevent that from happening. But the compensator is able to rapidly respond to system demands far better than using an unloading valve in addition to an accumulator in a conventional circuit. So if the pressure just drops off a little bit from standard pressure, sometimes as low as maybe just a decline of 50 psi, the pump will make up for that loss in pressure by delivering more flow to reestablish pressure. So it's very fast responding. So in the case of a gear type pump that's used with an older type of aircraft system with an unloading valve, that's not the case. Usually what we want to do is we want to hold that unloading valve in the kicked out position all the time, and we use the accumulator in order to do that. But again, very fast demand in case of the variable displacement pumps. Pump and loading valve pressure regulator is not required. Notice also what I've said in the next statement. The system accumulator is not required for the control of pressure surges, but may be installed for other functions. You'll remember that the accumulator has multiple features. If the pressure should drop off as a result of a tiny leak, the accumulator is the replenishing source. Also, too, if the pump should fail for the limited period of time that you have fluid available in the accumulator will kind of substitute for the pump for a brief period of time. So maybe for reasons of safety, it might be installed in order to kind of guard against a pump failure. So, but again, the compensator is actually very effective in controlling pressure surges. The other thing too, sometimes it's kind of a balancing act. If you have an accumulator installed where you've got a variable displacement pump, it sometimes makes the circuit a little bit sluggish in regulating flow, but it's the nature of the beast. When you've got an accumulator, realize that the accumulator kind of works like a battery in an electrical circuit, and you're really draining the voltage out of the battery before the generator replenishes the battery. The same kind of analogy with a variable displacement pump. You're going to have to bleed off the pressure that's in the accumulator before the pressure drop is enough to cause the compensator to make the variable displacement pump reestablish flow. So it's a little bit, you know, there's no free lunch. I guess that's what I'm trying to tell you. The principle of operation, there's really 3 different styles of variable displacement pumps. One style of variable displacement pump is called a demand type of pump. Another way of kind of wording it would be effective stroke control. We can change the stroke of the pistons, usually with sleeves that are mounted around the pistons, and I'll show you how that's done. There's another type of pump that has got a type of swash plate or cam where the angle can change on that swash plate or cam. And in doing so, it changes the stroke on the pistons. But that type of pump is called stroke reduction. Then there's another type of variable displacement pump that's called intake starvation. With that type of pump design, we intentionally starve the fluid flow coming from the reservoir. And what it does is it controls the discharge, since if you're limiting what comes into the pump, you're certainly limiting what can be displaced from it. There's really 3 different styles of variable displacement pumps. The conventions that they use to describe these pumps are similar to what you have for continuous flow. Variable displacement pump performance ratings, the ability to withstand back pressure without internal leakage. So sometimes, like on product literature, you'll say the pump is rated at 3,000 psi or 5,000 psi. Understand that, again, pumps don't really make pressure, but they have to be designed to work effectively against a back pressure. So where you've got some internal leakage. So the pumps are generally guaranteed or warranted to work in systems and sustain a pressure to whatever value that they have. But again, remember that pumps don't really make pressure. They just have to be able to withstand a working pressure against the discharge of it. With the engine-driven type of variable displacement pumps, they're usually rated in gallons per minute at a specified RPM. For example, at full flow at 3750 RPM, they may deliver 8 gallons of discharge. The electrically driven pumps, they're usually rated in gallons per minute at a specified pressure. So they might be rated at 8 gallons per minute, maybe at 3,000 psi. So nevertheless, just remember, pumps don't really make pressure. These performance specifications are built on the ability to sustain pressure against a back pressure that you already have in the discharge line. So, okay. A little bit about the leading particulars of variable displacement pumps. The key thing that controls the discharge of these pumps is called a compensator. It's a generic term, and there's many different styles of them, but they all operate in order to control the discharge of the pump for flow. The variable displacement pumps could either be engine-driven or electrically driven. In the case of Boeing aircraft, they have both. If you look at the pumps, they're the same pumps that are driven, but one is engine-driven and the other one is electrically driven from an alternating current motor. So they both work at the same time in order to supply fluid flow that can later be trapped to build pressure. Also a convention on many of these pumps, they have multiple ports on them. Obviously, you've got a discharge port that's connected into the pressure manifold. You've got a suction line that connects to the reservoir, and many of them have an additional line on the pump housing that they call a case drain. It's not a seepage drain that we use to detect shaft seal leakage. It's called a case drain. The case drain performs a function of cooling and lubrication of the pump by collecting fluid and delivering it back to the reservoir, sometimes also to the heat exchanger as well. It's mounted in the fuel tank of the aircraft. But as the pump is in operation, we have to keep the pump cool. So we need an exchange of hydraulic fluid that's going to provide for lubrication and cooling. The case drain on that pump is really attached to the internal portion of the pump, usually the case itself. And again, it provides for hydraulic fluid to circulate back to the reservoir for getting rid of heat in the pump. Many of the pumps have an integral bypass or a relief valve, and some of the pumps have multiple stages. If you look at some of the Boeing designs of pumps, they have an impeller that's mounted at the initial beginning inlet port of the pump, just at the inlet. The purpose of it is to help to prevent cavitation of the pump itself. What they're doing is they're supplying fluid flow through the impeller that provides the initial push on the fluid before it gets to the piston section of the pump. So you may have multiple stages, and again, it's just an additional aid to help prevent cavitation of the pump when it's in operation. Many of the pumps have a depressurization valve, and it'll be at the outlet of the pump. And the idea is to intentionally stop the discharge of fluid flow from the pump. It may vent the fluid back to the reservoir, or in some way, it may cause the pistons to stroke to a position where you have zero flow. But nevertheless, it depressurizes or at least takes the fluid flow, the discharge of the pump, and routes it someplace else other than the discharge. You may also have a fire valve that's mounted on these pumps. In the old days, when we were pushing hydraulic fluid that was flammable, this was a big concern. The last thing that you would want to do is further engulf the aircraft in a fire if one is started. So if you've got a turning propeller where you've got an engine-driven pump, sometimes we might have the necessity in order to prevent a fire, or at least prevent a fire from getting worse than what it was, by intentionally having a method of cutting off fluid flow at the inlet of the pump. So they may have a fire valve that might be mechanically operated or motor operated electrically, so that we can intentionally starve the inlet of the pump and prevent that hydraulic fluid that might be flammable from enhancing a fire that might potentially get worse. Also know that if we have multiple pumps that channel into a common discharge, they frequently have check valves mounted at the outlet of each of the pumps. The check valves are really part of the pressure manifold, but they're attached to the discharge of the pumps. The purpose of them is to isolate a pump that is maybe a broken shear shaft. So it prevents reverse flow, and it prevents one of the pumps that's got a broken shear shaft from operating like a motor. So if you didn't have the check valve installed, the operable pump would push fluid into the one that's lost power from a broken shear shaft, would motor it opposite the normal direction of rotation, and you'd be spewing fluid maybe even back to the reservoir. Or even worse, let's say that the case has failed, you're going to be losing fluid right out of a broken case of that pump. So again, you have to, generally, if they have multiple pumps that feed into a common manifold, there's a check valve there to prevent motoring the inoperative pump. That's why it's there. Many of the pumps, if they're variable displacement as well, and all three of the port fittings, there'll be disconnect fittings that are mounted there. The idea is it provides for interchange of a ground source of pressure in return in the event that you want to use ground power. So you may find the possibility of having a quick disconnects there. The other thing too is if you had to quickly replace a pump, the quick disconnects allow for really fast exchange of a pump that has failed with one that you're going to substitute in as good. So, okay, quick disconnects are there. This is the first type of pump that I want to talk about. This particular pump will be a demand type of pump. We have one of these in the shop. And the common trade name or brand of that pump was Stratopower. They still make them. I don't know if the company's been absorbed into another one. Eaton now makes a lot of the pumps for aircraft, but many people refer to this demand type pump as a Stratopower pump. This is a design of the late 1940s and early 50s, and you'll still see them used frequently today. They can be engine driven, they can be electrically driven. This particular one is mechanically driven, so it's engine driven. there's a shear shaft that's on it, and when you rotate the shear shaft, what you're doing is you're rotating a cam. So the cam has got a high lobe on it, or a high portion on one half of the cam. The other portion of the cam is low. So what's happening is you drive the drive shaft, or turn the drive shaft, the cam rotates, and it causes pistons to be pushed forward and aft on the cam. There's also shoes that hold the pistons in position, but what's happening is the reciprocation of the piston occurs because the cam rotates. Well, okay, so we've got a kind of a pumping action, just like the inline piston pump that we talked about last week. But what makes the pump kind of unique is that we can control how much fluid is pushed out of the pump by allowing an escape path inside of the pump when the pressure has been built up. The discharge port of the pump is here. This goes into the pressure manifold. The inlet side of the pump is attached here, and this comes from the reservoir. So the entire case of the pump is flooded with hydraulic fluid. When the pump is in operation and the drive shaft is turning, let's take a look at this particular piston. The piston is being pulled back because it's attached to the cam, and so as the cam pulls the piston back, an opening is provided in the front of the pump that allows fluid to enter into these hollow pistons. Okay, why does that occur? Well, you're creating a low pressure area by pulling the piston back. You're creating a void here, a low pressure area. So the fluid flow that's inside of the pump is allowed to fill the cavity of that piston. As the piston is pushed forward, eventually the opening that allowed that fluid to get in is closed off because you reach a portion of the pump housing where the fluid can no longer get in. As the pump continues to, or the shaft continues to rotate and the cam comes forward, eventually that fluid is now confined to the point where it pushes individual check valves open, and then that fluid flow is routed to the discharge of the pump. So again, in the cycle of operation where you've got a series maybe of 7, 8, or 9 pistons, each of the pistons in cycle is being pulled back, a port is open to the inside of the pump, and fluid flow is allowed to enter. Then, as a portion of operation, as the pump continues to rotate, eventually the piston is kind of closed off from this area here, so it's sealed from the inside of the pump. The only thing that can happen then is we can find the fluid enough so that as the piston is forced forward, the fluid flow is trapped and it can't go any further, so it forces the check valve open, and then it goes out the discharge port of the pump. Now, what we can use in this particular pump to control the amount of flow that comes out of the pump is a device called a compensator. It's really operated by system pressure. If you'll note, there's a tiny little orifice line that goes to a piston that forms one part of the compensator. So we have system pressure that's going to work on this compensator on this side of the piston. The other side of the compensator has got a fairly large, massive spring on it, sometimes 2 springs, and I'll kind of explain what that happens in a little bit. But you've got 2 kind of opposing forces. There are sleeves that are mounted around the pistons inside of the pump. The sleeves are able to operate in unison on a device called a spider. You can see how the spider's got multiple legs on it. You can envision at the end of the legs you've got these sleeves that are wrapped around each of the pistons. Well, when system pressure is low and we're delivering a lot of flow, these sleeves are going to be pushed very far back on top of the pistons. So what that means is whatever fluid is allowed to collect inside of the pistons, it's immediately going to be trapped and it's going to be pushed out ultimately to the discharge of the pump. However, when we build system pressure up, the system pressure will work on the compensator. It pushes the compensator to the right, compressing the spring, and what it's going to do is it's going to move these sleeves partially to the right. So what that means is as the pistons start to move forward, for a brief period of time, these holes that are at the very back of the pistons are going to be exposed. It allows a place for the fluid that would normally be trapped in the pistons. It allows an escape path back to the inside of the pump. So it's actually pretty ingenious how they did it. As system pressure continues to build, the compensator is pushed further to the right. the sleeves and the spider move a little bit farther forward. So as these pistons are being pushed forward, you have even more of an opportunity for fluid to escape to the inside of the pump. Do you see how this is kind of working? All right. Finally, when we build up to whatever the design pressure is for the circuit, the sleeves are pushed all the way forward, and then, or I should say the compensator is pushed all the way to the right, and then these sleeves that are mounted around the individual pistons are pushed as far as they can go. So in unison, as the pistons are being pushed forward, whatever fluid was allowed initially to enter is just provided a greater escape path back to the inside of the pump. So when we're in the zero flow position for the pump, whatever fluid the individual pistons take in, it's just being spit back to the inside of the pump. So again, you're really not regulating pressure so much as you're regulating what comes out of the pump. You're controlling the internal fluid flow of the pump as a response to system pressure. When the pressure builds up, it moves the compensator over to the right, and in doing so, exposes the holes at the back of the piston in order to bleed that fluid that with the piston had in it back to the inside of the pump. If the pressure should drop off, let's say it goes down to a certain point well below what the system requirement is, the spring is going to push the compensator back to some position so that these holes are then partially covered in the stroke of operation. So maybe for a portion of the cycle, as the pistons are moving, some of the fluid flow has gone back to the pump, but once these holes are covered by the sleeves, the remaining fluid that is in there is pushed out of the pump. The pump or the compensator and pump will respond to the demands of the system. That's kind of what I want to tell you. So if the system pressure drops off, well, we're able to trap more fluid that's inside of the pistons that we can put a force on to push out. On the other hand, if the system pressure is built up to a particular point, well, the compensator has been pushed as far over to the right as we can go. Whatever fluid the pistons have seen, it eventually just spit back to the inside of the pump. So pretty cool design. So we've got these relief holes, and again, the holes that we have inside of the relief holes, either they're covered or uncovered by these sleeves as the stroke of the piston develops. So we can spit the fluid back inside of the pump, or immediately cover them and push all of the fluid out to the outlet of the pump as required. There's a pretty good picture that shows you really a comparison of the two. Let's take a look at the pump when we're in the, let's see, this would be the full flow position of the pump. So this would be when the system pressure has not been built up, and what we have is low system pressure. So what we want to do is deliver full flow out of that pump. So they only show you two pistons, but you can envision we've got multiple pistons. When the piston is at the low spot of the cam, there's an opening from the inside of the pump that allows the inside of the pump pistons to fill with fluid. And the sleeve is positioned right here. So as soon as the piston is pushed forward, that hole is blocked off, and whatever fluid was trapped inside of the piston is being forced out. This would be the full flow position of the pump. When we build up system pressure, it's going to work on this compensator piston and be able to push it to the right. What that does is it moves the spider and the sleeves that are on those around the pistons and exposes that relief hole. So you can see in the zero flow position for the pump, the sleeves have been pushed all the way forward. So in this case, even though in the cycle of operation, the fluid was able to enter inside of the piston, as the piston was being pushed forward, that fluid flow isn't going to exit out the check valve of the pump. Where's it going to go back to? Inside the pump. Okay. Now understand, I've shown you just the two positions, the two extreme positions. It's important to remember that the pump will modulate to whatever is required to maintain system pressure. So you see two extremes, but understand if system pressure drops off a little bit, the sleeves will move just enough in order to compensate for that, in order to provide for additional flow. If there's a big pressure drop or a loss in pressure, the sleeves are shoved all the way back by the spring, and then in that particular case, you're delivering all the fluid flow that comes into the pistons right to the discharge side, to the outlet. Okay. Anything else about these particular pumps? Well, I should tell you that if you want to break the pump down into its integral sections, we have a mechanical drive section of the pump. We've got what we call a fluid displacement portion of the pump. We have a pressure control portion of the pump, and we have a bypass. The bypass of the pump is really our case drain. There's another section of holes that are forward in the pistons. These holes align with an annular groove that's part of the pump that delivers fluid flow back to the reservoir through a bypass port. These holes, as a portion in the cycle of operation, at some point will always align with that annular groove. So we'll always be delivering fluid flow back to the pump. The amount of pressure is minimum, but it has to be enough to overcome whatever pressure you might have inside of a pressurized reservoir. So again, it provides for an exchange of hydraulic fluid for cooling and lubrication of the pump, and that's why we have it. Anything else that's kind of unique? Well, let's take a look at the individual component parts that are here. Well, if we want to take a look at it, this would be the mechanical drive of the pump itself. We've got the shear shaft. I don't know that they necessarily show it here, but we've got the cam itself. We've got a stationary bearing that's in back of it. We have bearing surfaces that they call creep plates. They're made out of bronze. They're usually grooved in order to provide for lubrication that kind of goes around it. And we've got another interesting component part, many of these as part of the drive. It's called a nutating plate. I think you realize that in order to push the pistons forward, we've got the lobe of the cam that kind of does that. But how about for synchronizing the operation of all of the pistons at the same time? In other words, it's kind of an operation where some of the pistons are coming down and others are going up at the same time. The purpose of the nutating plate is to provide for the synchronization of those pistons. So as some of the pistons are actually being forced up, others, because of that nutating plate, are attached to the piston and a section of it that are kind of pulling it down. So it provides for coordination of the pistons. Sometimes also, many of these pumps will have springs that are mounted around the pistons. The purpose of the springs are to provide for the retraction of the piston or load the pistons against the cam. So again, it provides for kind of a constant force against the cam to prevent it from floating. So that's what we have. So this is the mechanical portion of the pump itself. Okay, the fluid displacement part of the pump. They've got the cam itself, and of course you've got pistons that are hollow. You've got an internal port that allows fluid to enter from the inside of the pump into the hollow pistons. We have bypass ports that are located here, and we've got check valves that are part of the housing of the pump at the outlet. There will be a check valve mounted at each of the piston discharge points, at least to a common area for the pump itself from the discharge. The intake for the pump, this would be connected to the reservoir, and the discharge port, of course, that goes back to the reservoir for cooling. The pressure control mechanism of the pump, it's really comprised of the compensator and the sleeves that are around the piston. So when the relief holes at the back of the piston are covered, what that means is whatever fluid is trapped inside of the piston is going to be forced to the discharge. When the holes are exposed, because the sleeves have been pushed someplace else, the fluid that would normally be trapped in the piston is provided with an escape path that kind of goes out, and it leads back into the inside of the pump. So it's a very kind of nifty way of kind of controlling flow from the pump. Here's a colorized view of the same thing. So it kind of shows you the operation of the pump. Very important to remember that the pump will modulate to maintain whatever the system pressure requirement is. So if it drops off a little bit, well, the pump compensates in order to make up for it. If the pressure drops off a great deal, well, the pump will modulate to deliver more flow with the intent of building pressure. So that's how the pump kind of works. Okay. Another two slides showing you the extreme positions of the pump. This would be the position for delivering flow on the left. The position on the right would be for the zero flow position. So the sleeves are completely covered by the time the piston reaches that point. So far, so good. All right, let's talk about another style of pump. Let's talk about a stroke reduction pump. These types of pump are a variable displacement as well, except what we have on them is a cylinder block that can change its angle. And remember when we talked about the Vickers pumps last week, some of them have got an angle on them, either maybe 15 degrees or 20 or 25 or 30 degrees or so. The angle that we have on the cylinder block compared with the drive shaft is really what establishes the stroke on the pistons. So the greater the angle, the more stroke that we have and the more flow that comes out of our pump. Well, with these types of pumps, what we can do is we can vary the discharge of the pump by changing the angle on that cylinder block. So if we flatten the angle out to where there's no angle difference between the drive shaft, you have zero flow. Where if we have a maximum angle on the drive shaft between that and the cylinder block, we've got maximum flow, and that would be the full flow position of the pump. Some of these pumps are really bizarre too. The yoke or the axis of movement forms the inlet and outlet of the pump. We've got two of them inside of the shop cabinet if you want to take a look at them. But they still operate by virtue of a compensator. The compensator, by the way, does the same thing as what you find in a demand pump. It controls how the discharge of the pump in terms of flow. So when we have the requirement for full flow with the attempted building pressure, you're going to find the maximum angle has been established on the cylinder block, and then system pressure begins to build and limited amount of flow is required. The cylinder block axis of move, or the axis will change. Ultimately, where we don't have any stroke on the pistons just revolve inside of the cylinder block, but since you don't have any stroke on them, nothing is being displaced from the pump. So nothing is being pushed out. So the compensator is located here, and it's usually connected to a connecting arm or a link. And again, as system pressure builds, it pushes on, the system pressure works on the compensator against the spring and begins to drive the link up and pulls the cylinder block to a zero flow position. Remember as well that it doesn't go immediately from full flow to zero flow. The idea is it will modulate in normal operation to maintain whatever the normal system pressure is, and that's all that you have. Okay. Same kind of conventions too. You'll very frequently find a shear shaft on these things. You'll also find seepage drains that are on them, and that's about all. This is kind of the theory of operation for them. If we can vary the stroke that we have on the pistons, what we can do is we can change the displacement of the pump. So what you see down here is kind of a simplified view of what's happening with a compensator used for it. The system pressure really works on the piston compensator, and in doing so, what it does is it drives the cylinder block to a lower position in order to control the discharge of the pump. Some of these things receive pressurized fluid from an accumulator, or at least may work on that. But again, there are styles of variable displacement pumps. This one has got an integral relief valve that's incorporated with it too. But again, it senses, the compensator senses system pressure in order to be able to vary the discharge of the pump. Let's take a look at this little video here. Okay, so we got a swash plate or a variable cam, and you can see what this one does. This is a little bit different in design, but here's system pressure down here that is able to work on the compensator, and right now it's a computer animated type of thing. You can see the inlet and discharge side of the pump. When there's a big angle on this plate, what that does is it kind of controls the discharge of the pump. When we don't have any stroke on the pump, you're not delivering any fluid out of the pump, so you're at the zero flow position. So that would be, this would be at when we built up system pressure. Maybe, I don't know what this represents, bar or whatever, but you would be at the zero flow position. And then if we drive the system where there's a requirement for flow, where the pressure goes to zero, you have maximum angle that's on the pump. So works really well. And Here's one from Parker. They show you component parts of one that have been broken down in a three-dimensional view. That's the yoke that pivots in order to change the stroke of the pistons. So this one's got a yoke on it that kind of changes its position, and the cylinder block just kind of goes along for the ride. Discharge of the pump. Here you can see the fluid flow. The blue is obviously from the reservoir. So in the cycle of operation, as the pistons are being pulled back, you create a low pressure area that fills with fluid from the reservoir. And as the pistons are pushed forward, fluid can't be compressed, so it has to go off the discharge through the discharge side of the pump. There's the action of the compensator. We're going to show you that in a minute. But when the system pressure builds up, it works on the compensator in order to change the effective stroke. So in this case, we're now at zero flow. And then when we need flow, well, okay, there's low pressure in the circuit. The compensator responds by delivering more flow. We've got a spring on the other side that kind of works in opposition to the compensator.
How fast does it rotate?
The design speed for most of these is 3750 RPM. That seems to be the common speed anyway. Most of them don't push out a great, even in the full flow position, they don't push out a great deal of fluid. And the way that they compensate for that is by turning them at pretty high RPM. Leading particulars on one type of pump anyway. They can be run at higher RPM, but there's some danger of cavitation. So what they tell you is that in order to avoid cavitation, you have to have sometimes a pressurized reservoir that's used with it. You want to run it really fast. Particulars for the connection points of the inlet, the discharge, and the case ring, they tell you what sizes of ports that they have. And these things are relatively heavy. Anything else? Not really. Fairly efficient pump, 96% efficient, and it looks like the maximum stroke angle, just like any of them, usually about 30 degrees at full flow. Any more stroke angle that you might have on them, it makes the pump too inefficient because of the torque required to turn it. So, mounting position, unrestricted except that the case drain line must be connected to the reservoir in such a manner that the housing remains filled with oil during all operation. Okay, so whatever the case drain port is at, it has to be mounted up. Okay. But this is one that has been an exploded view of what we have. We've got the same pump that's in the shop. And again, they can be electrically driven or they can be engine driven. It doesn't really matter too much. Okay. Here's a Kellogg pump, kind of the same type of deal, but just a different manufacturer, but it's got a swash blade in it or a variable cam that allows for the discharge of the pump to change as well. The compensator that we use to control system pressure is located down here at F, and again, it sees system pressure in order to make it operate. If you trace the line that goes back here, here's an outlet check valve that we talked about earlier. This prevents reverse flow in the event that the shear shaft should break, and it prevents the pump from being motorized. But the discharge of the pump is allowed to travel to the compensator, and the compensator sees system pressure. The other side of it has got a spring that works opposing the compensator pressure or inlet discharge pressure. The fluid flow from the compensator goes to a stroking piston. The stroking piston is pushed back on an arm, and that in effect controls the discharge of the pump. They've got a case pressure check valve installed inside of the pump as well, just like in a lot of gear pumps. So this provides for a lubrication path for the case drain that eventually will lead back to the inlet of the pump or the reservoir. So when we're trying to lubricate the pump through its clearances, that provides for the exchange of hydraulic fluid for cooling. Bearing locations are located in the pump, so it looks like the cylinder block rotates, and that's what carries the pistons along. Okay? But it's a Kellogg type of pump. Another Kellogg pump. If you want to see how some of these pumps kind of operate differently, you take a look at something like this. This is a variable displacement pump. We'll get to there in a little bit, but take a look maybe at something else. Another view of the same type of pump. It's a stroke reduction pump. So again, we can control the pistons and their positioning so that we can control the discharge of the pump. Another type of pump. This one's an intake starvation pump. We don't have one of these here, but they do exist. My old A&P school in Illinois had one, and it's kind of a marvel that it doesn't cavitate, but it does in fact work. The theory of operation is that the pump limits the discharge simply by closing off the inlet from the reservoir. They erect a wall in sections at the inlet, and that stems the flow of fluid from the reservoir. The compensator that it works on is located at the inlet of the pump, but it still responds to system pressure. When the system pressure builds up to a predetermined level, it works on a piston that builds up a circular wall at the inlet of the pump and begins to starve the pump of fluid. So that's why it's called an intake starvation pump. The cam is a fixed cam in it. The pistons are able to reciprocate back or forth, but apparently the pump does not cavitate. It takes in just enough fluid, even when we're in the zero flow position, so that it doesn't cavitate on itself. And this shows you different positions of that wall or that sleeve that they erect at the inlet of the pump. In the full flow position, you get unrestricted flow that comes from the reservoir. So obviously what's allowed to fill the cavities of the pistons fills them completely. And then as pressure begins to build, there's a sensing line attached to the compensator. What it does is it pushes the piston up progressively and then eventually blocks the inlet of the pump. It's a sleeve type of piston that's really got multiple surface areas on it. So as the system pressure begins to build, there's just enough surface area that's exposed on the piston so that only a moderate amount of starvation of the pump occurs. But once the system pressure builds up higher, it exposes another surface area of the piston that it finally erects the wall to just a trace or a dribble amount that hydraulic fluid is able to get into the pump for lubrication and prevent cavitation. So this would be the zero flow position of the pump. Okay. I got a drain line coming out of this thing. Obviously the sensing line that builds pressure, they have to have an exchange of fluid or coming back out of it in order to be able to make it work. So you get a drain line that comes out on the other side. This is kind of a unique pump. This is a stroke reduction pump, but I picked this out of a Lockheed service letter that went into extreme detail about the hydraulic system on the P-3 aircraft, the Lockheed Electra. They use the same type of pump and hydraulic system on the Lockheed 188, L-188 aircraft, but this one particular one is not engine driven. It's actually electrically driven. They use an AC motor in order to drive the shaft of the motor, but it's a variable displacement, and it would be a stroke reduction type of design that's in it. These things are really heavy, and I can't remember the exact reason why Lockheed went to this particular design. All of their hydraulic pumps in the P-3 aircraft are all electric. There's no mechanical pump in the aircraft. You may say, well, is that a problem if we have loss of electricity? Well, maybe not so much if we've got a standby battery aboard the aircraft. But more importantly, I think there's a concern too. If all engines should fail, they're not dependent upon having an operable engine in order to operate the pumps. So, but again, it's kind of a trade-off. I guess their greatest concern would be loss of engine power, and if they had all mechanically driven pumps, well, they're out of luck. The pumps won't work. So they elected to drive all of their hydraulic system via electric pumps. There's also something kind of unique about the P-3 aircraft too, the Electra. These particular pumps are sensitive to frequency vibration because of the electric motor. And in order to damp the frequency, what they've done is they've installed Quinn-key tubes as part of the pressure manifold. And I'll read to you what it says here. The hydraulic pressure pump surge damper, specially designed hydraulic pump pressure surge damper incorporated in the hydraulic system. These installations are located in the hydraulic service center next to the hydraulic pumps. The installations, commonly referred to as Quinn-key tubes, reduce pump noise and vibrations, thus modifying the AC hydraulic pump surge. The installation consists of rigid lines arranged to resemble the slide portion of a trombone. Each AC hydraulic pump installation has two of these plumbing arrangements connected together to reduce aircraft hydraulic pump vibration and noise further and eliminate pulsations. Tube length is critical because it is tuned to 1/2 and 1/4 of the wavelength of the offending aircraft hydraulic pump. So again, the one way to kind of reduce the pulsations the pump might produce, they've installed these long these long pieces of tubing that are cut to a precise length in order to control the discharge or control the vibration. Yeah.
Two questions. One, why are they using, in this case, is AC aircraft or alternating current?
It's alternating current, I think.
Why are they using alternating current?
It's much more efficient in terms of delivery.
Right.
If
For the same amperage, you'd have to have a lot bigger.
Lots of voltage, yeah.
Right.
Okay. Or at least we consume lots of amperage. The formula for watts is E times I.
Right.
So when we use AC power, we can manipulate the voltage, but we have to have transformers in order to do it. So it gives us the option of being able to raise the voltage to an extremely high level and control the amperage, but get the required amount of wattage that we need for the circuit. We use the same kind of idea usually in several other things. Like one thing that kind of comes to mind would be an anti-ice aircraft windshield. With an AC windshield, they consume a tremendous amount of wattage per square inch of heated surface area. We could use DC power to do that, but the amperage requirement, it would drain the battery or drain our electrical system of amperage just too quick. So what we do is we play a game. We use an AC system, alternating current, and by doing that, we can vary the voltage with a transformer. We can make the voltage go really high, and we can then control the amount of the wattage requirement, and it only requires a very small amount of amperage. So really effective. Oh, by the way, too, this thing called the Quinn-key effect. Did you ever smash your finger with a hammer and watch what happens to your finger? You kind of see the pulsations that kind of go on, or sometimes when your heart beats, if you're really careful, you can look like it's your thumbnail or fingernail. You can see the blood blanch out of the capillaries. That's called the Quinn-key effect. What they're doing is the same thing with the tube. So what they're doing is they're allowing the tube to kind of pulse a little bit in order to absorb the vibrations that are occurring. It's kind of a unique method of controlling vibration. It's called a Quinky tube. This is the simplified flow schematic out of a P3 or a commercial L-188 aircraft. They had options. In some aircraft, they had an optional pump or a spare pump that might be in the service, but they're all electrically driven. It's kind of interesting to see what they drove from those electrically operated pumps. The source of pressure to operate brakes, integral steers for the aircraft itself, windshield wipers, aileron booster. These are really enhancements to the flight control to make them powered. So aileron booster, elevator booster, rudder booster, and wing flaps. And notice also too, for redundancy, they're being supplied off of separate pumps. So they're all commonly going into the circuit in order to maintain a degree of safety and redundancy. Main landing gear actuation and in-flight brake, nose landing gear actuation and steering, and they've got a method of starting the aircraft with a compressor, but they're using a hydraulic motor in order to do it. So they use hydraulics for that purpose as well. So I'll see if I can, I think you've got it too. If you want to look up, I think I've got it in the AVIM library somewhere. I've got this service letter from Lockheed. You know, sometimes as a mechanic, you have an opportunity to take a look at a few things from a service manual, but you don't know the reason why they did what they did. Sometimes the product literature or the service letters that Lockheed and other manufacturers produce, they give you the answer to a really important question. It answers the question why, you know, why they did a thing a certain way. So if you look at the architecture for a lot of aircraft, it explains the reason why they did it. You won't get that information from the service manual. You'll just get basic information on how to service the aircraft or possibly perform maintenance functions, but it doesn't solve the mystery of why they did what they did. The motor-driven variable pump looks like this. Lockheed kind of looked at it this way. Ease of installation. You can mount these things pretty much any place in the aircraft you want to, since they're electrically driven. Also, too, they're not dependent upon engine speed varying. Since they're electrically driven, they're driven at one speed of the electric motor, whatever the output shaft actually produces. And you're not dependent again upon an operating engine. If the engine should fail aboard the aircraft, no harm, no foul as far as the pump is concerned. The pump should continue to operate. Like a lot of other Boeing designs as well, they use a stage of initial push on the fluid with a centrifugal boost pump in the internal to the pump. It does contain pistons in it, but again, it provides the initial push of fluid. The disadvantage, it's heavy and it's big. And this is kind of what it looks like. So, but it's a stroke reduction pump, and I'll show you a little bit about what it has on the inside of it. This is a cutaway view of what you have. You've got a three-phase electric motor that's encased inside of a housing that hydraulic fluid is allowed to circulate in. And again, in order to keep the motor cool, what they've done is they've got a jacket mounted around the electric motor. So the electric motor, the heat is dissipated to that jacket of hydraulic fluid. The initial stage of push on the fluid is provided by a centrifugal type of impeller. They call it a supercharger, but nevertheless what it does is it prevents cavitation of hydraulic fluid before it gets to the inlet of the pump. So if we pick up the inlet of the pump here, this is from the reservoir. Some of the fluid flow is delivered around that initial stage of the pump, the centrifugal stage. It goes into a cooling loop around the motor in the housing and the jacket, and it's delivered inside of the pump, and then eventually it's going to go back to the reservoir via the heat exchanger. So that provides for cooling of the electric motor, also provides for cooling of the pump internally. This is really our K-string. Some of the fluid flow is going to be destined to the pump though. That fluid flow that comes off of the impeller also goes inside of the pump, and it's going to be directed to the cylinder block where the pistons kind of reside. They can't show you in this view the tilting of the cylinder block, but I'll show you a view of what's happening in it in order to kind of make it work. The compensator for controlling the tilt on the cylinder block is located here. The compensator has to be furnished with a sensing line. The sensing line senses discharge pressure. So again, when the system pressure has been built up, you won't have any displacement of the pistons or the cylinder block. It'll be virtually straight with the shaft of the pump. However, when system pressure builds up, the system pressure works on the compensator, opposing the spring of the compensator. It begins to tilt the cylinder block over so that we develop stroke on, or I should say, we're able to control the stroke of the pump or the pistons of the pump. In the book, I think they mentioned also it says 15 to 20 psi above the existing reservoir pressure. So if we've got a pressurized reservoir that many aircraft do, whatever fluid flow is being used for cooling internal to the pump, it has to be able to overcome the pressure that you have for reservoir pressurization. The reduction gears, it cuts down the speed to 3,200 RPM, and that'll be a constant speed that we have on the shaft of the pump, for the electric motor. What else? Colorized view of kind of the same thing, and this shows you what's actually happening inside of that pump in 3 different stages of operation. The first picture shows you the full flow position of the pump. The compensator is mounted here, and the cylinder block that's tilted at its full deflection is here. The angle, the max angle that they'll have on it is roughly 30 degrees or so. In this position, the system pressure is, you're going to have full flow with the intent of building system pressure up. There's some of the flow from the pump also, again, is going back to the reservoir for cooling. And it says 8 gallons per minute at with a sensed pressure of less than 2,200 psi. So anytime that the system pressure is being monitored through that pressurization line that goes to the compensator, the cylinder block was going to be in its full flow position, and we're going to have full flow being delivered into the pressure manifold with the intent of building pressure. So we've got maximum angle that's on the pump. The compensator controls a piston that's got multiple, how can I put this, surface areas that vary. And ultimately, when the system pressure builds up, the compensator was going to be pushed out slightly. It's going to be pushing on a stroking piston, or at least a piston that we have that's connected to a shaft that goes to the cylinder block. In this position, we're delivering about 8 gallons per minute at a sense pressure of anywhere from 2,200 to about 2,950 psi. And there's a variation too, plus 50 psi, minus 0. But you don't have enough, quite enough pressure to completely push the piston over. When the pressure finally builds up to, maybe about anything beyond 2,950 to a max limit of about 3,000 psi, you fully push down the spool of the compensator. And what that does, it exposes a surface area internal to a sleeved piston. This gives you more surface area in the piston. That rapidly moves the piston to the zero flow position. So nothing comes out of the pump. This is what makes the pump very fast in operation. You'll notice that the system pressure was set at maybe about 3,000 psi, and all it took was an additional 50 psi or so for this compensator to finally react for you. Finally, it caused the cylinder block to flip to the full zero flow position. So it's extremely fast acting. So it's a big advantage. This is why when there's just any minor interruption in system pressure, the pump is able to compensate really fast, because the compensator and the piston has got multiple surface areas on it in order to be really responsive. They call one of the piston surface area, they call it the constant horsepower piston area. Then they've got another piston area that they call the cutoff position. This is actually the sleeve portion of the piston that system pressure kind of works on. But that's what they have inside of the pump. Okay. So a lot of Boeing aircraft, just kind of a colorized view. I don't know where the heck I got this from. It may come from your new airframe book. But Again, remember on many of these pump designs, they may have an integral impeller, and it prevents cavitation of the pump, in addition to maybe also having a pressurized reservoir. But it provides for an initial push on that before it finally gets to the piston section of the pump. And again, kind of interesting. The compensator for it, the compensator is always there in order to control the discharge of the pump. This one is a stroke reduction pump too. You can see that it's got a compensator that can control the angle of that the swash plate in order to control the stroke on the pistons. This one's engine driven. Case pressure check valve, again, that provides for cooling and lubricating the pump. The fluid is eventually exchanged back to the reservoir, or sometimes the inlet of the pump. Picture from your airframe book, I think it's really the same pump. Blocking valve, if we want to starve the pump of fluid intentionally, or discharge of the pump, sometimes the blocking valve can be closed, sometimes by via relay or a solenoid in order to be able to do it. Stroke reduction pump as well. Normal pumping operation, you can take a look at a lot of the illustrations, you can kind of figure out what's happening in them. Here you can see that they've got the compensator mounted here. The compensator controls flow to a stroking piston. They call it an actuating piston. When the pressure builds up beyond a certain point, the discharge pressure pushes the compensator down. It delivers fluid flow to a stroking piston, an actuator piston. That pushes the yoke back and it controls the stroke of the pistons, ultimately to zero flow. And then when system pressure bleeds off, maybe the system pressure is lost, the spring is going to work on this side of the swash plate or can. It pushes the stroking piston back, it reestablishes the stroke on the pistons, and again we deliver more flow from the pump. I think you got whether the pump yoke angle kind of works, you figured that out. More angle means more flow. For depressurization, what they use is system pressure to kind of disable the pump initially. They've got a depressurization valve that's solenoid actuated. So when they provide electrical power to this particular valve, it pushes the spool up. It directs system pressure to the piston head on top of the compensator. The compensator then is pushed down. System pressure then finds a route that goes over to the stroking piston and makes the piston go to the zero flow position. At the same time, hydraulic fluid under pressure is it's admitted to the top side of this blocking valve, and it blocks additional system pressure from leaving the pump, or any fluid flow from leaving the pump. So it can be cut off that way. Variable displacement pump, stroke reduction too. Got an actuator piston on it that controls the angle that you have. Depressurization solenoid, again, it just provides for zero flow when we don't want any more flow to come out of the pump. Foot valve, a common term that they use for the case pressure check valve in many of these pumps. So if you see that, it's the same thing as what would normally be called the case pressure check valve. It vents fluid back to either the inlet of the pump or to the reservoir for providing for internal lubrication of the pump through seepage. Variable displacement pump as well. This one's electrically driven, and that's what we have. This is a picture I stole from somewhere. It shows one of these stroke reduction pumps, and the actual pivot point for the pump is here, and yet another one on the opposite side of it. This also forms the inlet and outlet of the pump. The valve plate is located way up here, and the pistons are forced to ride on shoes that are part of the swash plate. This is really kind of a marvel of engineering too. The shoes that the pistons ride on are hydraulically balanced. They've got tiny little areas underneath the pistons that are grooved, and it provides for, as the pump turns, it provides for minimum torque and balance of the pistons as it revolves. The rotating mass is kind of sensitive to movement, so what we want to do is we want to provide for an internal balance out of the pump. They do it hydraulically. Same kind of conventions too. If there's a sleeved area over the pistons, Usually there's an annular groove that's mounted on each of the pistons. It provides for locating or squaring the pistons inside of the cylinder bore. So in order to prevent contact, we don't use rings. What we just use is a film of hydraulic fluid in order to keep the pistons centered inside of the bores. This is one taken apart. This shows you the swivel that's connected to the piston. Ultimately, it goes to the shoe anyway that's connected to the swash plate. And again, grooves around it, and that kind of provides for keeping the cylinder or the piston square or at least supported inside of the bore. And the bottom side of the pistons, a lot of times there's a kind of little micro grooved areas in this thing. It provides for balance of the pistons and the swatch plate. Okay, so far so good? Question?
So on the pumps that have a drive shaft, they can be driven with either a gas turbine engine or a piston powered engine.
You can drive them with any mechanical type of drive.
So if you're using a gas turbine engine, what is hooking to the spline?
Oh, they've got gear reduction. You've got the accessory drive,
Oh, okay.
just like a regular piston engine. How about we talk about something else? Let's talk about this. It's called a RAT. It's an acronym that stands for Ram Air Turbine. This is our last resort. And what I mean by that is if we've lost all of our hydraulic source of pressure, we have a operable source of pressure, but it has to be deployed. So what we have is a pump that's usually driven by relative wind. It's called a ram air turbine. It's mounted on an arm assembly, usually stowed in the aircraft. The deployment of the arm is usually under spring pressure. So obviously they would have the arm mounted in such a way that even if you lost hydraulic pressure, there would still be a way to deploy it. So it works kind of like the arm assembly works kind of like a switchblade. So when the pilot wishes to deploy the rat, the spring extends, and then the arm of the rat is positioned into the relative wind, carrying the rat with it. So some of these things are kind of different. Sometimes the ram air turbine could be used for an emergency generator. Sometimes it could be used for a hydraulic pump. Sometimes it could be used for both. But it depends on the design of the aircraft actually to what it does. But Boeing uses it, Lockheed uses it. It'll provide essential hydraulic service, but obviously it's small in capacity. So it's not going to restore everything. It's going to supply those things that are considered to be essential for safe landing of the aircraft. Okay. Here's a couple pictures of one. This is on an F-105. They're mounted a lot of different ways too. Sometimes they're mounted on a pallet that's exposed to the relative wind. Sometimes they're on an arm assembly that does the same kind of thing. Let's take a look at this. Here's a 787 with one deployed. This is part of the test, I think. See that thing hanging out the back? Right there? They can be commanded to be operated. In other words, you can deploy the arm assembly to expose the rat. And also, too, on many aircraft, it's a function of throttle position. If the power lever for the aircraft is retarded past a certain point, that would cause the rat to be deployed as well. So. They can be checked on the ground for operation by back driving them with hydraulic pressure. So if we've got a ground service cart on the available, we can use that as part of the pressure manifold. We can at least verify the operation of the pump by motoring it, and I'll show you that kind of next how it's done.
For such a big plane, wow, how come they don't have multiple rats?
How come?
They don't have if it's a last resort, wouldn't they have more than just
Oh,
one?
they got multiple pumps, but they always have to provide for some eventuality that they didn't think of. So, you know, it's kind of unusual to have all engines fail, all electrical pumps also fail. but I guess there's a possibility where it could happen. Maybe part of the architecture of the aircraft at under some remote condition, the entire pressure manifold is severed. So it'll provide for at least maybe a little bit of flow.
So they design it assuming I would think that they would design it assuming that the plane is just totally dead.
Yeah, this is, like I said, last resort. So that's all that you got. I've got a schematic too, I'll show you in a little bit. This is from an A320, and again, they can back drive it in order to check its operation. They just make a motor with hydraulic pressure. They usually mount a cage around it when they do this because, again, it's kind of an operational hazard. And again, it can be retracted on the ground. And again, what you're doing is you're putting a force back on the spring again, so that for the deployment, the spring is going to take it back out. Also, too, to stow these things, there's usually an index mark that's provided on the arm assembly and on the motor or on the pump itself, and that's important. Sometimes when you have to retract them, obviously if the blades are mispositioned, it's not going to go back into its designated spot. So sometimes they provide like a little index mark on these things, and what that provides for is so that it can be retracted fully inside of its retraction space. I may have a video for that too. Let's look that up real quick. Oh, by the way, too, they're variable displacement pumps. The way that they vary the discharge, or at least control the output of the pump, the blades are variable pitched. So they've got a governor that's inside of the pump itself, and the way that they can kind of control the speed, or at least the speed of the pump anyway, in its discharges via a governor. So it's got a flyweighted governor inside of it. Picture of it. I've got an article someplace, I don't know if you want to see a little bit more, learn a little bit more about them, but kind of interesting devices. All right. Next, let's talk about another kind of emergency device we may have aboard the aircraft that's related to